Hello, this is Simon from Reigate Maths, and this is another video in the Year 2 A-Level Maths content for integration. This is the second video in our series on differential equations. This one is focusing on finding particular solutions. If you haven't yet gone and watched the video on general solutions, I strongly advise you do that so that you have a background as to what to do for these questions. So let's jump straight into an example, something like this. Find the particular solution to this differential equation given that y equals 2 when x is 2. So you can immediately see that this differential equation we do not need to do separation of variables because it's already in the form dy by dx equals a thing. So let's look at some terminology. These are specific points, or are specific coordinates. The general, or the term for these is boundary conditions. Because they give us the boundary for our equation. So you may need to use this term relatively frequently, particularly when you start getting into modelling with differential equations, which will be another video. So let's have a look at how we answer this question. So the first thing you have to do when answering particular solution DEs is find a general solution. Okay, so that is the first thing we have to do. Now with this one, we've got that dy by dx is the square root of x minus 1. So again, because it's in the form dy by dx equals a function of x, we know that it means that y is going to be the integral of this thing. Now to make it easier for us to integrate, let's write it like that. And you can see, unlike in the previous video when we went through this in a little slower, you actually don't need to write the integral of 1 dy equals. You can just write y. This question we now use the reverse chain rule because we can see the derivative of the bracket is 1, which is what's on the outside of the bracket. So we can just integrate using our rules. So this tells us that y is x minus 1, increase the power by 1, and then divide by the new power, plus c. So let's tidy things up before we start putting numbers in. So we get that y is 2/3 x minus 1 to the 3/2 plus c. So this is stage 1 done. We found our general solution. Here. Step 2 is then use the boundary conditions. To find c, or to find your constant. So we know that when x equals 2, y equals 2. So we can put those in. 2 equals 2/3. 2 minus 1 to the 3/2, which is going to come out nicely, plus c. So we can see that 2 is going to be 2/3 plus c. C is going to be 4/3. So that is stage 2 done. We haven't quite finished the question. The last thing we need to do is actually answer the question. See, the question is find the particular solution to the differential equation, which means we need some function that has x and y's in, which we don't have yet. So the last stage is write down the particular solution. Okay, so therefore, particular solution is y equals 2/3 x minus 1 to the 3/2 plus 4/3. And we're done. So you can see that this example, although the differential equation didn't need much messing around with, it was a relatively simple, just first order differential equation, the whole process is still quite long. And that's the thing with differential equations questions. It's something that students find very difficult, is how full on these questions are. They are very, very long and typically worth quite a few marks. So be very careful and do take your time. Okay, don't forget, aiming for a mark a minute in the exam is all well and good, but this is the type of question where you can use some of that buffer time that you have. Because don't forget, at least with Pearson or with EdXL, the exams are 100 marks, but they're 120 minutes. So you've got 20 minutes to play with, which ideally you should be using to check your work. But if you need that little bit extra time for things like this is the type of question that you're going to use it for. So next example we're going to look at is a little bit more complicated because it's going to involve that separation of variables step, but it's still following this sort of system of instructions. Find the general solution first, use the boundary conditions to find your constant, then write down the particular solution. So here's our next example. Please pause the video now, have a go, and then come back to see me go through the answer in a moment. Okay, so we've got that dy by dx equals x squared e to the minus 2x. So step 1 is solve the differential equation. So here we need to separate variables. Because we've got a mixture of x's and y's on this side and a mixture of x's and y's over here. So let's do that. So moving the y's over to this side, we get y to the minus 2. Now notice how I'm not writing it as 1 over y squared. You can do, but they're the same thing, and this is what we'd need to do anyway to integrate it. Remember, 1 over y squared doesn't integrate to a ln, 1 over y would. And then we're just left with e to the minus 2x on this side. So we then integrate both sides. So this goes to minus y to the minus 1, because it's a standard integral. You increase the power by 1, divide by the new power. Here, it's our e to the x, so we get minus a half e to the minus 2x plus c. So now we have more or less our general solution. Yes, we could tidy it up a bit more, but there's no real point for now. So we now use the boundary conditions. Because yeah, once you've integrated and got your constant, you can use this wherever you like. Use it where it's going to be easiest. Okay, don't faff around with trying to rearrange first if you're just going to have to rearrange again to find C. Maybe you may as well find C as quickly as possible so that it makes it easier. So when x equals 0, y equals 1, which tells us that minus 1 to the minus 1 is going to be equal to minus a half e to the 0 plus c. E to the 0 is 1. So we get minus 1 is minus a half plus c. So therefore, c is minus a half. We then substitute that back in. In order to then eventually rearrange to get our equation. So therefore, minus 1 over y is minus a half e to the minus 2x minus a half. Now, although this question hasn't asked us in the form y equals a function of x, this one would be much nicer too. Because it's got lots of minuses, lots of fractions, it tends to be a little bit more unpleasant to rearrange, or to look at if you don't rearrange. So we're going to do that now. So we can see they're both over a half, and there's a bunch of minuses. So let's multiply through by -1 and sort this out so it's one fraction. So we get e to the -2x plus 1 all over 2. Now, we can then just flip both fractions to get our final answer. Doing this is really useful when we get onto modelling, which will be the next video, because typically we might use different letters than y and x, but let's say x is time and y is your population. There's no point leaving your equation like this if you then want to work out the population after 100 days. This is a much more useful thing to do because you can just stick the numbers in straight away and it tells it to you. So that is a more difficult example using everything that we've done so far in differential equations. We've separated the variables to integrate. We've then used the boundary conditions to find our constant, and then we've rearranged to get a usable equation. In the next video, we'll be looking at modelling. So we'll look at how to form differential equations and then how to solve them. But thank you for watching.